Two blocks of masses MA and MB are connected by a massless string that passes over a pulley as shown below. The coefficient of kinetic friction between MA and the inclined plane at angle theta above the horizontal is mu k. When the system is released from rest, MB moves upward, so let's indicate that, and MA moves downward on the incline. So indicate all directions of forces acting on each block. So for part A, let's draw the free body diagram for mass A acting on the block, which is this one. I'm just going to keep note that the acceleration's direction would be like this on the side. And then for a free body diagram, let's think of what all forces will be acting on mass of A. So I'm going to draw an axis parallel to mass A. So it's it's slanted, so I'm drawing an axis aligning with the box, the object. And this is the y-axis, and this is the x-axis. This is going to be the positive direction because I want acceleration to be positive. So what you should include on a free body diagram, you don't have to include this, but I just like to draw it just to see it visually. So there is a force due to gravity going straight down, which is basically just mass times gravity, or also known as the weight. And there is an upward tension in the string. So we're going to denote that as RT, as well as it mentioned the kinetic friction between MA and the inclined plane. So there is a kinetic friction that's also pulling on opposite to the direction that the mass A is moving. So we're going to draw another line with an arrow and writing FK, force of kinetic friction. And of course there is a normal force on the block perpendicular to its inclined plane of mass A. So that's this direction. See, it's going perpendicular to the ground of mass A. So that's the normal force. So this is our free body diagram with all the forces for mass A, and the free body diagram for mass B, the tension in the string acting on it. This is mass B. You don't have to draw a dot, but I like to do that. And we have a force due to gravity acting on it. And that's it. And acceleration is obviously in the positive direction going up. So part B. If mass A is equal to 8 kilograms, mass B is equal to 3 kilograms, and the angle is 50 degrees and mu k is 0.3, determine the common acceleration of the two blocks and the tension in the string. I'm going to set an equation in the x direction for force of mass A. So for mass A, we can see that we denoted that we want acceleration to be positive, right? So whatever forces are acting on this side will be negative. So in the x direction, we only have a force acting in the positive x direction, which is mg sine theta, and theta is the degree that is given, 50 degrees. So we will write the following as MA g sine theta minus the tension and the kinetic friction force. Minus tension minus F of k is all equal to ma, because Newton's second law is F is equal to ma. So, and a is in the positive direction, so it's positive. And now let's write the equation in the y direction for mass A. And that is just normal force, and that will be positive, minus mg cosine theta, which is in the y direction. So normal force of A minus mg cosine of theta is equal to 0, because there is no acceleration in the y direction, so this is why it's equal to 0. We can solve for normal force, which is equal to m mass of A times gravity times cosine of theta. So we have two equations right now, 1 and 2. Now let's write the forces of mass B in the x direction, which is 0, because it's only moving in the y direction. So that was easy. Force of B in the y direction, since acceleration is positive in the entire system, that means tension will be the positive force, and the force due to gravity will be in the negative. So we write as tension minus force, I'm just going to write mass, of B times gravity is equal to ma. So we have our third equation. And we can rewrite this to solve for tension here, because it'll be easier to do it than here. So tension is equal to mass of B times gravity plus mass of B times acceleration. I forgot to take note, but on the side, remember that F of k is equal to mu times normal force, and in this case, it's the normal force of mass A. So F of k will be 0.3, because that was given to us, times the mass. Since normal force of mass A is equal to this, it'll be 8 times, okay, I should have rewrote this here. I'm going to rewrite it here. F of k is equal to 0.3 times 8 times 9.8 cosine of 50, which is equal to roughly 15.12. So that is our F of k. So now when we do this, we will get an equation that looks like ma g sine theta minus m b g mass of B times gravity plus mass of B times acceleration minus F of k, which is equal to mass of A times acceleration. So if you rewrite it, now I'm going to take this and add it over. Now you can combine like terms over here. Divide this out and plug it into your calculator. So if you rewrite this as numbers, it would be 8 times 9.8 sine of 50 minus 3 9.8 minus 15.12 all over 8 plus 3. And that is equal to, if we plug it in our calculator, roughly 1.41 meters per second squared as our acceleration. Now previously we solved that tension. Plug this back into equation 3 and find tension. So mass of B is 3 times 9.8 plus 3 times 1.41. So T will be equal to roughly 33.63 newtons.